Yeah. Thanks for staying for us. It is great to be here, and really excited to talk about a cool topic. That's really important, and I'm sure you've heard many times here at the show about the need for greater sustainability. No one's going to solve sustainability problems by themselves. It's got to be a collaboration, but everyone has to do their part. We want to talk about some of the things that AMD is doing to help bring sustainability to the data center and the big impact that can have. My name's got it. My name's Jim Green, Director of Technology Marketing in the Server Division at EPIC. I'm very pleased to be joined by Tawfik here, one of our super smart engineers and power architects that can really, so we're going to give you kind of a 1-2 punch here. Talk about some of the things that we're doing and the products that we're delivering to help improve sustainability in data centers. Tawfik's going to give you a little peek under the covers to tell you how we're doing that and some of the specific things and some of the challenges that arise and how we rise to meet those challenges. So we're going to start with a little chat on common data center trends, some of the power goals that AMD has set for ourselves, and then some of the things that we've done to optimize that power very specifically down at the circuitry and transistor level. Is there a question? Okay, sorry. The topic here is what is driving this. Data centers today already consume a massive amount of power, right? It's between 1% and 3% depending on where you look globally. Here in the United States, I think the DOE is saying it's between 1% and 2%. That is an enormous amount of power. How do we help? And a lot of that is going to data centers, right? So the data centers is consuming 1% to 2%. That's a lot of power. How do we help mitigate that? Because there's a constant need based on how people are growing their workloads to pull that up. And that's historically been the case, and right, the industry's done a pretty good job at keeping it down to that 1% to 2% level in the United States, given the massive amount of growth in data and compute infrastructure that's going on here. So the industry's done a pretty good job, but now the challenges are really going to get hard because we're no longer doing the incremental growth of kind of the traditional workloads. We're adding some stuff into there, particularly, the two main culprits are going to be AI and supercomputing type things that are coming downstream and getting into the enterprise. That's really going to change the dynamic because the requirements and the consumption, the power and performance needed for those are well beyond the traditional kind of step function incrementalism here. If you look at AI compute, the requirement is doubling every 2 years in terms of the amount of infrastructure that needs to go do that type of processing here. That's great, 2x, much higher than Moore's Law here, right? So that's going, Moore's Law is every 2 years roughly, and it's kind of sliding out a little bit lately, but the requirements for the compute infrastructure are doubling every 3 to 4 months. And that's not a good trend line, right? And we can see that gap is going to continue to grow. On the supercomputing side, the number of flops that are being consumed by some of these critical workloads, again, we're talking about doubling every 1.5 years or so, much faster than the rate of Moore's Law type of growth. And now we're getting into the breakthrough machines like Frontier that are getting to the exascale, and we'll see more of those systems coming online. Massive amount of growth in that type of infrastructure. And it just keeps going, right? So if we want to look at the amount of memory that's being consumed, everything we're lighting up in inside that chassis is consuming power, generating a lot of energy that we have to A, provide, and then B, provide the wherewithal to get rid of it, right, through the HVAC system. So it's really an enormous amount of burden that's going on here. Because when you think about servers, typically, I think the average I've seen mostly is roughly 40 to 45% of the data center power is related to server infrastructure, storage infrastructure, networking infrastructure, and then 45% is HVAC for said systems, right? I mean, that's a lot of juice. Anything we can do to take one of those, we could take the power generation side and consumption side down, that's also going to have a nice impact on our ability to reduce the amount of energy needed for cooling. So what is AMD going to do about it? Our goal is to have a 30x improvement in efficiency, performance per watt, across through 2025. And that's across our CPUs and GPU families, right? So those really compute-intensive engines, how do we take the juice down there? The good news is that's better than the industry trend. That's a good goal. The better news is we're beating that goal currently, right? So if we look at the EPIC 3 and then the EPIC 4 generation, we continue to push well beyond that ratio. So we're trending in the right direction. We want to keep that up because it's a really important thing. No matter what region we talk about, no matter what system vendor, every watt counts, right? So they want to see what can you do to take that power down without compromising performance, without burdening me with some other big change, because that's the other alternative. We're working to say, hey, how do we implement this change without giving you a massive architectural transition? We did it under the covers. So we take the approach with the EPIC 4 family to create the 4C variant. And essentially, what it does is an optimization for power efficiency, right? We're not going to give up the performance. We're going to be able to get more dense, and more power efficient through a compaction of the technology. And it's not just on the traditional compaction, which comes with process nodes, right? We actually took the time to redesign and relay out and hand code circuitry so they can actually reduce the waste, reduce the length of traces. They did a lot of real optimizations to be able to drive down that power, but not lose the ISA, right? So same instruction set. Not lose anything on the L1 and L2 cache. We'll take a little bit of the L3 cache away for workloads that don't really need that. So you're not really compromising performance for most of your workloads. You don't have to change your software, and you can get more efficient, energy efficient architecture. It shows up in the numbers, right? We can run traditional workloads and running kind of the standard server-side Java spec benchmarks, deliver really compelling performance because we can give you a lot of cores in that same area. We can give you a lot of performance, and again, these things aren't being impacted by the lack of L3 cache here. So roughly 2.7x what the industry is seeing from some of the competitive architectures that require software changes, moving, for example, to an ARM-type architecture. And even compared against the best x86, we're still roughly 2x better. Really, so you can show you can get with much better performance without sacrificing the power, without sacrificing the infrastructure in your environment. Taking that one step further, we took that same Zen EPIC 4 Zen 4C processor core and put it into another package. This one leans in on the single processor preference that is emerging from customers here. Said, hey, if we could put that into a different socket from the Genoa family that we launched earlier, we could do things to help further reduce the power consumption of the platform. So that's when we launched the 8004 series. It's the Zen 4C cores, little less streamlined. So it's a little more streamlined on some of the infrastructure, so not as many memory channels, not as much PCI lanes, et cetera. It's really for that super dense. A lot of customers are tending to use this as kind of an edge computing device because it gives you very high performance, strong performance, but not the typical expandability. And of course, it has much less power, right? So you can see we could do some real interesting things here to take the TDP to well below half of where the current 9004 kind of latest and greatest platform is. We could take that power consumption and operating ranges way, way down so we can be NEBS friendly, could do things so you can now start to do things with fanless type systems and really still get performance. So these are the types of things that we want to continue innovate and iterate with our OEM partners to deliver more efficient systems in data centers, whether it's a hyperscale, whether it's a traditional data center, or whether it's an edge type data center. I think there's opportunities to continue down that path to deliver more and better efficient infrastructure. Tawfik's going to tell us how we're going to do it.
Thank you. Thank you, Jim. Thank you.
Thank you.
Oh,
I'm sorry.
Thank you. Thanks, Jim. And like Jim talked about our roadmap, our products, and I think throughout this theme of this conference, you've seen, there are a lot of terawatts at stake, all in the data center, and the GPU plays a big part of it. GPU, CPUs, the semiconductors, basically, big part of those terawatts. So I'm going to take you now a little bit down from the terawatts to the microwatts, because it's all start there, and talk to you about some of the things we do, to achieve those power savings. Now, power is a horizontal function, and it actually runs across the entire product lifecycle, from concept to architecture to RTL, design, testing, everything. Basically, power touches everything. And it's really a platform thing. And like our team, when we pursue a watt, we pursue it. It doesn't matter where it comes from. If it comes from AVR efficiency improvement, from a GPU, it's actually a watt. So we pursue it everywhere. And there's absolutely no way I can talk about this entire thing. In the previous talk in our panel at noon, I touched a little bit more on the power delivery aspects and the power management and how those play a big role in actually achieving power reductions. Here I'm going to talk to you a little bit, on the more advanced stages, like a little bit on the RTL design, how we can save power in those, so you can look at here, for example, this is on the RTL optimization. So it's a very simple, the capacitance is simply CV squared F. Okay, and so power is proportional to the capacitance. The switching capacitance, does this? Oh no, I think, excuse me. Okay, I can use maybe. The switching capacitance proportional to the power. If you look on the right side, basically, of this curve here, I'm showing you utilization versus CAC on the y-axis, meaning the switching capacitor, versus the block utilization in the x-axis. Block utilization, basically, like if you look at the block on the chip, the question is how much that block is doing work. To give you just an example, if you're running for 100 clocks, and that block is particularly engaged in 20 of those, you'd say I have a 20% utilization. And clearly, if the block has 0 utilization, you're not doing any work on that block, your power should be 0. Your CAC should be 0. And so if you look at, that's the lower end, the 0. If you're doing maximum utilization, you're doing a lot of work. That's your peak power on that block. And the utilization is very, very high. Our job in RTL is to take this parabolic curve and make it actually like the red linear curve. We want CAC to be proportional to utilization, basically. That's how we minimize power in the RTL. And some of the very simple techniques that we use, some of them industry standard, some of them actually custom-made at AMD. A very common technique is clock gating, right? And the clock gating happens at multiple levels. You could do it at a very coarse level. For example, you could gate the entire unit if it's not doing work. Or you could go very fine granular at the flop level, look at every flop. And we do clock gating, we do roughly 4 to 5 levels, actually, quite a number of levels of clock gating. Now, there is some tricks to that. It's not as simple as it sounds, because anytime you do clock gating, for example, you're stopping clocks, so you're increasing your DIDT. And when you increase your DIDT, that tends to raise your voltage up. Raising voltage up is very bad for power, right? So although you're bringing C down, if you raise your voltage up, you actually lose quite a bit of that power. So it's a very careful trade-off. And if you're doing very gross kind of things, that's very easy to check in post-silicon. You just turn the thing off, turn it on, you measure, and you make your trade-off, average power versus the IDT. If you have millions and millions of gators, at the flop level, and we have a lot of those, then you have to figure that out correctly by simulation, because you can't do millions of off and on, in post-silicon. And this is where, in my call to action to OCP, that's where I think we can help in getting the CAD tool to do that type of trade-off a little bit better. Now, moving a little bit quicker here, other things, like what we call switching activity-informed placement. In other words, you look at the signals, you know what's switching, and those signals that are switching a lot, you bring them closer together in your layout so that you minimize the power in the interconnect. And if they're not switching, you don't care. That's OK to place them actually quite far. Other things like pin swapping, meaning the pins that have large capacitances, large capacitances, put the lower switching activity on those pins. Again, there's a lot of those techniques. I can't go through all of them. But each one of them, typically, we have a lot of engineers working at the microwatt level, making sure, we get to this curve. We don't leave anything unturned. If there's a single gate, that can be gated, that's not gated, we gate it, and so on. And it adds up. It adds up to sometimes 20, 30% of the total power of the chip. The last one I'm going to talk about a little bit is this multi-VT, where you have a menu of devices. Now, the reason you need those menu of devices is because generally performance is very, very important. If you have a single circuit, that doesn't mean the clock. The entire chip actually clock, goes down. So we have a menu. You negotiate those with your technology team. And then it's all about having very good automation. And what that automation does, it looks at every net on that chip and asks itself, what kind of transistor should I use here? Because every transistor has a timing versus power characteristic. If your chip is running 3 gigahertz, you don't need to run any circuit at 3.1 gigahertz, right? That's a wasted power. So we go on every circuit, actually, and just place just the right transistor among a menu of multiple transistors to minimize power. So let me go even faster than that. So in summary, I think like my colleague has shown you, we are committed to the 30x. We're doing a little bit better than that. This is very important. You've seen a lot of talks today showing you there are terawatt at stakes in those data centers. And it all starts really with microwatt level optimization. That's how you get all your terawatts. So what's my call to action? I think what we want from the OCP, something that OCP is very good at, basically standards, okay? We do need protocols for chips to share power budget with the software, so the software can manage those chips. And we do need better CAD and better industry capable of making those trade-offs, say, between the IDT and average power. And with that, I think I should conclude. Thank you. Thank you very much. Yes. Oh, I can.
Yep. Thank you, and everyone who held out to the last. And that concludes our presentations for today. Thank you for attending the summit this year.
These are all the toughest people.
Thank
Yep.
you very much.
Survive.